You've been told the universe runs on rules. Predictable, elegant, unbreakable. Now imagine drifting alone between galaxies. No stars, no dust, just a black, endless ocean. Your instruments say space is smooth and empty. The equations agree. For a moment, it feels safe. But then the rules begin to bend. Your clocks disagree. Directions lose their meaning. Light itself behaves like it's forgotten what it is. Because scattered across the cosmos, there are places where our physics does not merely struggle. It breaks. In this journey, we'll visit 8 of them, each stranger than the last. And the final one will change how you understand reality itself. This is Deep Space Decoded. I've spent months digging through the data, the papers, and the arguments. What you're about to hear is what survives that fire. Let's begin. Number 8. Number 8. The Event Horizon of Sagittarius A** in 2022. The Event Horizon Telescope collaboration released the first image of Sagittarius A**, the supermassive black hole at our galaxy's center, in the astrophysical journal Letters. That glowing ring is not the hole itself. It's the last place light can still orbit before falling forever. The event horizon. To scale it, if Sagittarius A** sat where our Sun is, its event horizon would stretch roughly to Mercury's orbit. A dark sphere big enough to swallow 10 million Earths. General relativity says spacetime here is so warped that all paths point inward. Quantum theory says information can't simply vanish. At the horizon, those two pillars disagree violently. We do not know whether reality preserves information or quietly destroys it. We have never crossed an event horizon. We have also never proved that information survives it. Number 7. Number 7. The Big Bang Singularity in 1970, Stephen Hawking and Roger Penrose published their singularity theorems, proving that, under reasonable assumptions, general relativity predicts a beginning. A point where density, temperature, and curvature become infinite. Wind the cosmic clock back, and everything you know is crushed into something smaller than an atom, then smaller than a proton, then smaller than any length physics can currently describe. Here, our equations explode. Infinity appears where there should be numbers. We can describe the universe a fraction of a second after this moment, but not at it. Whether there was a before or whether time itself ignites here, remains unresolved. We have not seen the singularity. We have also not shown that it was never there. Number 6. Number 6. Inside a neutron star in 1967, Jocelyn Bell Burnell detected the first pulsar at Cambridge, an ultra-dense neutron star. Today, observations with NICER on the International Space Station and the Green Bank Telescope have mapped their masses and sizes with precision. Imagine a star more massive than the Sun crushed into a sphere the size of a city. A teaspoon of its matter would weigh as much as Mount Everest. At these densities, atomic structure collapses. Protons and electrons merge into neutrons, and beyond a certain depth, we don't know what happens. It could be superfluid neutrons, exotic quark matter, or something we don't yet have words for. Our best nuclear theories disagree in the very place the universe is running the experiment for us. We have not sampled the heart of a neutron star. We have also not proved that normal matter survives there. Number 5. Number 5. The quantum vacuum in 1948, Hendrik Casimir, working at Philips Research Laboratories, predicted that two uncharged metal plates placed very close together in a vacuum would feel a mysterious force. The Casimir effect was later measured with exquisite accuracy. In human terms, we call it empty space. Between those plates, it should be truly nothing. Instead, quantum field theory says it seethes with virtual particles flickering in and out of existence. Their restless fluctuations push the plates together. Now stretch that to cosmic scales. The same vacuum energy should blow the universe apart catastrophically. Our calculations overshoot reality by about 120 orders of magnitude, the worst prediction in physics. We have measured vacuum energy. We have also not understood why it is so impossibly small. Number 4. Number 4. The edge of the observable universe in 2013 and 2018. The Planck satellite team released the most detailed maps of the cosmic microwave background, revealing the universe as it was 380,000 years after the Big Bang. Those maps show a horizon, about 46 billion light-years in every direction. Beyond that, light has not had time to reach us. If Earth were a point, this sphere would be our cosmic prison wall. We can never see past it, no matter how long we wait. The expansion of space itself is dragging distant regions away faster than light can bridge the gap. Inflation theory suggests there is far more universe beyond this horizon, possibly an infinite amount, with potentially different structures, maybe even different physical conditions. But we can never test it directly. We have mapped our observable bubble. We have also not confirmed anything outside it. Number 3. Dark matter halos. In 1970, Vera Rubin and Kent Ford measured how fast stars orbit in the Andromeda Galaxy at the Carnegie Institution. The outer stars moved too quickly. Something invisible was holding them in. Imagine spinning a pizza. At the edge, the dough should fly off unless there's enough mass to hold it together. Galaxies behave the same way, and according to visible matter alone, they should have torn themselves apart long ago. We now think every galaxy sits in a vast halo of unseen matter, outweighing normal atoms 5 to 1. We've built detectors deep underground, launched satellites, and smashed particles at CERN, and still, no one knows what dark matter actually is, or whether we've misunderstood gravity itself. We have measured dark matter's pull. We have also not touched a single dark matter particle. Number 2. Quantum entanglement. In 2022, Alain Aspect, John Clauser, and Anton Zeilinger received the Nobel Prize in Physics for experiments on entangled photons. Particles linked so deeply that measuring one instantly defines the state of the other, even when they are far apart. Think of two coins tossed on opposite sides of the Earth. Each is random until it lands. But in entanglement, when you look at one coin and see heads, the other reveals tails, with perfect correlation, as if they decided together outside space and time. Quantum theory allows this. Einstein called it spooky action at a distance. No signal is traveling faster than light, yet the universe behaves as if separation is an illusion. The boundary between here and there simply dissolves in the mathematics. We have closed every loophole we can find. We have also not explained what entanglement really is. Number 1. The quantum gravity frontier. In 1974, Stephen Hawking used quantum field theory on curved spacetime to predict Hawking radiation, black holes slowly evaporating by emitting particles. His paper in Nature tied together general relativity, quantum mechanics, and thermodynamics, and exposed a fatal inconsistency between them. On one side, general relativity treats spacetime as a smooth fabric. On the other, quantum theory insists that at the Planck scale, about 10 cubed to the power of 5 meters, everything must fluctuate and come in discrete packets. When we try to write one theory that respects both, infinities explode through our equations. String theory, loop quantum gravity, causal sets. Each offers a different vision of spacetime grains or vibrating strings, but none has decisive experimental proof. The places where gravity is strongest and quantum effects are unavoidable, inside black holes, at the birth of the universe, just above the Planck length, are precisely where our instruments cannot yet reach. Reality is running a code we do not know how to read. Most people assume physics is finished. You now know we are still missing its deepest layer. So the next time you look at the night sky, ask yourself, are these stars obeying laws we truly understand, or just rules that mostly work until they break? This is only one chapter of the story. The next episode dives into the most extreme black holes we've found, the ones that forced theorists back to the drawing board. If you don't subscribe, you will miss that part of the map, and it's the one even scientists argue about. Which of these 8 places unsettles you the most? Leave the number below.